All right, so where we left off on the previous episode of chemistry lecture, we were talking about molarity, and it's how we measure the concentration of solutions. And you're going to have to do this quite a bit over the course of the year, um, where you find the molarity of a solution, which is just moles of solute over liters of solution. So we did a quick example. I will tell you this. One of the things that you're going to want to do when you're in college, if you're a science major especially, if you're a history or econ major, it's a little different. But if you're a science major, you really want to find a professor and work in her or his lab, because that's the best way to get experience, to know that you actually like what you're doing, but also it gives you a great recommendation if you have a professor who can vouch for you, right? So one of the best ways that I found to get a job with a professor is to really know how to make solutions, because most chemistry is done in solution. So if you know how to make really good solutions with really precise molarities, that's something that you can sell to a professor. Say, look I'm really good at making solutions. I know you do a lot of solution chemistry. So if you hire me for either credits or for money, I can really help you out. So credits is a great thing to do. Most colleges offer summer research experiences. So you can apply for a grant to get, I don't know, I think back when I did it, it was like $5,000 for the summer, but now it's like 6 or 7, I think. So you can apply to get a grant for this amount of money to do research for the summer for a professor. And it was awesome for me because I lived in my apartment with my friends over the summer, and I worked like 8 hours a day, and I had a little money, and it looked really good on my resume and stuff. So this is just like down the road what I recommend you guys doing. Getting good with a professor or two, do research with her or him, and knowing how to make solutions makes getting that job easier. So you're going to see a lot of molarity particle views. So on the left, I have 0.2 molar NaCl. If we assume boxes are equal volume, how many particles of each should I represent in the box on the right? Well, I know this is 0.2, and I have 1, 2, 3, 4, 5 Na plus ions, and I'm going to assume I have 5 Cl minus ions. So if I want to represent 0.08 molar NaCl here, well, how many of each should I write in? So think about it at your table for a minute. Talk about it with the people at your table, your partners. How many Na pluses and Cl minuses should I draw in the box on the right to make that molarity? Okay, so somebody raising your hand, what do you think? Alexi. 4 and 4. Why do you think 4 and 4? Yep. Yep. No, the ratio. That's exactly what you want to do, but your numbers are off. You would not want 4 of each. It would be 2 of each. Yeah. So that was like a nice logical way of thinking that you did, Thomas, is like it's a little less than half. So I probably can't have a partial part of a particle. Half would be 2.5, so we can round down to 2. But you can also know that this is 40%. 0.08 is 40% of 0.2. So you take 40% of the particles on the left and put them in the right. So the AP is really stressing this particulate view of you being able to visualize what's happening in solution and what that means in terms of molarity. So concentration, how much stuff there is in a given volume, and as we went from a higher concentration to a lower, we have less particles on the right. Okay. Now, how are we going to make a solution with a given molarity? Oh yeah, Ian. So the question is about, from the slide before, should you round down or round up? You will never, it should always be an even number, right? So in this case, it's an even number because you have 5 on the left, 40% of 5. You have 5 of each on the left. 40% of 5 is 2, so it comes out to a whole number. Yeah. Now, if this were 0.1, right, then it would be exactly half, and then you'd have the rounding, but we'll avoid that. Okay. So, making a solution with a given molarity. 1, determine the volume necessary. So, say I need, and I'll put we'll do an example in a minute. So this is what Mr. Hamill and I do. When we prep labs, the first thing we do is we figure out how much stuff we need in terms of volume of solution. Determine moles of solute required. So once you know how much volume you need, well, you can determine the moles. So what equation do we use? We use our molarity equation. So remember, molarity equals moles times liters. Moles, over liters. So if you multiply your desired volume times your molarity, you get moles. So really all you're doing is you're multiplying your number from part 1 times your molarity, and you know how much you need. Then you measure out your solute. At no point have I touched anything about the solvent yet. I've determined the volume of solution necessary, but I haven't done anything with the solvent yet. I've just determined how many moles of solute I need, and now I've measured out the solute. And this is, for our uses, this will generally be a solid, but can also be, hold on. Generally be a solid, but can be a liquid. All right. So the best way is now to put solute into a volumetric flask. And you guys remember from our first lab of the year what the volumetric flask looks like, right? It's the one that just has the single gradation, just the one line. And your last step is to carefully add solvent until it reaches the line. Yeah, Wesley. So the question was, will the solvent always be water? In real life, no. For us, yes. So a lot of the interesting chemistry that goes on at the college level and then graduate level and beyond takes place in organic solutions. So a lot of times it will be organic solutions. So the one that we used was, what did we use? Methylene chloride is a common one that people use. It used to be used to strip paint off of like chairs and wood and stuff. Then they found out how toxic it was, and so it's no longer used for that. But yeah, so for us it'll almost always be water, but it doesn't have to be. So let's do an example. Somebody throw out a number. So I need 2 liters of, and another number, of 0.275 molar, what do I need? NaCl solution. How do I make it? All right. So this would be a typical kind of question. I need 2 liters, and I have my molarity. How do I make it? Well, I've already step 1 is check, done. Now to determine moles, oops, that should be molarity. I take my volume, which is 2 liters, times 0.275 moles per liter, and I get 0.55 moles. If I did my math right. Somebody who does mental math quickly. So right here. Yeah, but moles over liters is the same thing as molarity. The question was about the moles versus moles over liters. So moles per liter is the same as molarity. All right. How do I figure? So I want sodium chloride. Well, sodium chloride is a solid. How do I measure out 0.55 moles of sodium chloride? Do I have a balance that measures moles? So what do I need to do? Convert it to grams. Absolutely. So yeah. So 0.55 moles times, well, what's the molar mass of sodium chloride? So sodium is 23, chlorine is 35.45, so 58.55 grams. And I'm pretty good at mental math, but not nearly good enough to do that. If somebody has a calculator out, like, or a phone out in front of them that they want to do this number really fast for me. Alex is on point. It's going to be somewhere around, what, like 32-ish, 33-ish? We'll just say 32.2 grams. So I would measure out the 32.2 grams. Pour solid into volumetric flask, and then add water until volume equals 2 liters. Right, so remember the solute actually takes up some space. Not a huge amount of space, but enough that I can't just dump in 2 liters of water. Because if I dump in 2 liters of water, I'll be left with more than 2 liters of solution, and I won't have the right concentration. Yeah, I had a friend whose wife was a postdoc, and they went through all this work to publish this really important paper, and when she was editing the paper, one of the grad students had measured his concentrations wrong throughout the entire experiment from start to finish. So they had this paper that they thought was ready to go. They had to scrap it. So like years of work down the drain because somebody could not make a good solution. Sucks. But so I mean, this woman was a postdoc, the wife of a friend of mine. So she just moved on to the next thing. You know, it's tough. Oh, the person who messed up. I don't know. At that point, I lost the story, but probably had to spend more years in graduate school to learn how to make solutions, which is something you guys should be able to do very soon. Okay, how can I tell if a sample of matter is pure or if it's a mixture? So one thing I can do, check physical and chemical properties. So, for example, pure substances have a set boiling point. Oh, that's ugly. Set boiling point, melting point, density, color, etc. All these things that we call intrinsic properties, things that it doesn't matter how much of the substance we have. So if I put something on, I put a liquid onto a burner and I measure the temperature and it boils at 105 degrees C. Do I have pure water? No, because the boiling point isn't 100, right? So you can check the physical and chemical properties, or you can attempt to separate materials. A pure substance can't be separated. Into other components. Whereas a mixture can be separated. Right. So if I have pure water and I try to separate it, well, I can't separate anything out of it. I could do a chemical reaction that would split the water into hydrogen and oxygen, but that's not the same as just trying to attempt to separate the materials using, I don't know, we'll leave that because there are some chemical methods. But if I have a mixture of, say, salt and water or sand and water, there are things that I can do to separate out those materials from one another to get back to pure substances. So we are going to now study separations. I took as a chemical engineer, I had a whole semester course called separations, which was just how do you take things and mix them, break them apart. So mixtures can be separated based on physical or chemical properties. What are some properties that we can separate based upon? If you wanted to separate something, how might you be able to do it? Heat it up, so different boiling points. We're going to touch on that one. Yeah, Wesley. You can drain. So if there are different phases, you can separate based on the different phases. So burning it would go into here. You could do a reaction, but I don't know that we want to call that a separation necessarily. But it's good thinking. Yeah, sifting. So if there are different phases, you can sift it. Or particle, I'll put that. Particle size. That's a property. You can also separate it based on polarity. Dun, dun, dun. So I'm going to put, you can separate it based on density using, we're not going to talk about it, but using a centrifuge. Centrifuges are really cool. So getting back to, I have half an hour and I only have, okay, we're good. I can go back to story time because I think this one is actually kind of valuable. Not all my stories have value, but this one is one that has value. Connects back to what I was talking about before. I did an independent study my second semester junior year of college, where I studied, so you know when you get your blood drawn, there's like a little polymer at the bottom. So you get your blood drawn into a tube, there's already something in that tube. And that tube, what happens is that the polymer, it looks like a little gel almost, in that tube, when you put the blood through a centrifuge, that polymer goes in between the red parts of your blood, like your blood cells and stuff, and just the serum, which is just like the clear stuff, right? So that polymer gets in between the two, so you can draw out the blood cells easily. So it was a really cool project. We studied like the physical properties of the different polymers that were used to maximize their utility. But so you centrifuge out the more dense stuff, like your blood cells, go to the bottom, and the less dense stuff, like the serum or just like the liquid, stays at the top. And then you can measure whatever you're looking for in the blood. So centrifuging is a way to separate particles, separate mixtures, but we're not really going to talk about that one too much. We're going to talk about this, and this. We're going to do a lab soon. I think what Mr. Hamill and I decided is we're going to let you guys do like a choose your own adventure. You're going to get a choice of 3 different labs, and you'll get to pick one of them. And one of the ones that, and then you'll have to present your data to the class. So one of the ones that you're going to do is on the polarity piece right here. Okay, so the most basic way of separation, I think, is filtration. So this is separating a solid, and generally that's solid. Wow, that looks like, I have no idea what that word looks like. You know, generally a precipitate from a liquid. So a lot of reactions that you'll do will be what are called precipitation reactions. So you mix 2 solutions, come together, and you get a solid that forms based on the solubility of the compound. Okay. To get that compound out, that precipitate out, you use filtration. So how does this work? So you have a filter paper, which is porous. So allows liquid through, but not solid. Okay. So you slowly pour sample into the filter, or onto the filter. The liquid flows through, and the solid stays behind. What you notice here is that there's also a vacuum pump. So we only have one source of vacuum in the room, which is right here, right up front. So it's just kind of fun. So the vacuum doesn't do anything differently other than it just speeds up the filtration. Now the thing is, most of the time you're going to want to collect the solid, but sometimes you're actually going to want to remove the solid and use whatever you collect down here, right? Say you have some contaminant in your solution that you want to filter out, and you want a nice pure sample left, you would actually filter out the contaminant and collect the solution that's left behind. So it's not always that you're collecting what's on the filter paper. It's just a method to separate the two phases from one another. This is not, I know in honors chem you do a lab with this, right? Yeah. We definitely did not in Chem 1 because this process kind of sucks because you're left behind with like a wet, gooey mess on the filter that you need to dry over a period of time. If you do this quantitatively, which means you're trying to figure out exactly how much mass you have of solid, it's hard because if you have any water left behind, it's going to make your mass look too high. And it's also hard to scrape all of the solid off the filter paper and get a really good recovery. So this is not a particularly efficient means of separating, but it's a very good, quick, and dirty means of separating the two. Yeah. So the good question. That was a really good question. So is this something you're supposed to do once or multiple times? It could be multiple times. More common than that, though, is that you pull. I can speak. You pour your solution out, and then you're still left with solid behind in your beaker or whatever. So then you have to use DI water and rinse your beaker out that has the solid left, and then dump it again and dump it again. Ideally, this collects all of your solid, right? But you may have solid left behind in the beaker that you need to further collect. All right. Okay. Any questions about filtration? All right, paper chromatography. This is separation based on intermolecular forces and polarity. This is one of the other Choose Your Own Adventure labs. This was one of my favorite labs that we did last year. What you do is you're given a bunch of markers, wet erase markers, and you have to figure out what dyes are present in those wet erase markers. So what you do is you put small amount of sample right above the solvent line. So I'll put it in my place small amount of sample just above solvent level. So in the case of the wet erase marker, you just put like a dot, right? And so you have special chromatography paper. This should say special paper. Special paper. And so if you put paper in water or other liquids, what's going to happen? Yeah, so the paper absorbs the solvent. And we call this our mobile phase because it's moving. So that solvent slowly starts going up the paper. And then it hits your sample, right? And so that sample starts moving up, moving up, moving up, moving up, moving up. Is it my bad handwriting or is it? Mobile. Yeah. I'm going to go with it's my terrible handwriting. All right. Okay. So the paper absorbs some of the solvent. Solvent starts crawling up, hits your sample, and the components of the sample travel different distances based on polarity. And the unit we use for this is called RF, which is the fractional distance traveled So what does that RF look like? Well, orange. To calculate the RF of the blue dot, we would measure here. So how far did it travel? Call that D1. Over how far the solvent traveled, which is D2. So the RF would be equal to D1 over D2. So it's always a number, it's always less than 1. It's 1 or less than 1. Yeah, Wesley. So I was just about to get. We'll get more into the stickiness when we get to the next slide. But it's how compatible they are. So if I have water as my solvent, and in my mixture I have something very polar and something nonpolar, well, the polar thing is going to want to travel with the water, right? So the polar one will travel very high up, whereas the nonpolar one might only move slightly, right? So it's how compatible it is with the solvent. We'll tell you how far it is. And remember, there are levels of polarity. We tend to think of it in terms of like, this thing is polar, this is nonpolar. But remember, there are, we talked about polarity briefly in terms of Debye's, which is just the general overall polarity. So there are different levels of polarity that you can have. It's not polar or nonpolar. It's a continuum. All right. Last 4 slides. Column chromatography. This is extremely useful. This is used in every chemistry lab I've ever worked in. For like every commercial chemistry lab I've ever worked in. So what you do is it's similar to paper chromatography. I always spell chromatography wrong. Chromatography. It's similar to paper chromatography in that it depends on polarity. But the sample can be retrieved. So if you use paper chromatography, you cannot get that sample back, right? Once you put it on the paper and it travels, you can't get it back at all. You can't collect it. Here, you can harvest each component of your mixture. So the example they use here is a black dye. What you can't see here is that there are beads in the column. So these little spheres, these very tiny little spheres that they pack in tightly. My first boss ever said he spent 2 of his 5 grad school years just making chromatography columns and packing them tightly to make sure they worked right. So we have these beads here, and then we pour in our sample. So this is a mixture of, at the time we don't know how many different dyes, but we can see that it separates based on the components and their polarities. So let's say these beads can be polar or non. The beads themselves can be polar or non-polar. Let's say the beads were polar. Right? Beads are polar. What part of the dye do you think is the least polar? Which part of the dye is the least polar? Is it the yellow, the red, or the blue? What do you think, Thomas? Okay. Okay, so the yellow comes out first and the blue comes out last, right? So the theory is the blue is nonpolar because I have polar beads, so it would not be attracted to the beads. Okay. Right theory, wrong outcome. Right? So if it's not attracted to the beads, what's going to happen when I dump it in? It's just going to flow right through, right? It's not going to be attracted to the beads at all. Right? So if I have polar beads, well, the yellow is the least polar. because it has no attraction to the beads, or very little attraction to the beads, so it can just flow right through the column. Whereas the blue, well, the blue really likes the beads. It's happy being with the beads. It's attracted to the beads. So the blue would be the most polar. Okay? So you have to think about what your intermolecular forces are. Let's draw. I'll give you guys a second. I'm going pretty fast because I want to make sure I finish. But so I'm going to blow up the internals of a column. So we have lots of beads. They're packed really tightly. I gave myself too much space. So I'll just erase the bottom. And I'm going to, you know what I should do? All right. So this is what it looks like. And I'm just going to zoom in on this one bead. Zoomed in. So on the surface of that bead, I can put different things on the surface. So let's say I put something that's very nonpolar, right? So that bead is covered with nonpolar molecules on the outside. This is definitely not to scale because the molecules would not be that big compared to the size of the bead. But you get the idea of like, it's covered in nonpolar substances. Well, if I pour in something that has two components, let's just say it has water and gasoline. I pour it in. The water flows through quickly. And the gasoline, which I'll make red, the gas flows slowly because it's actually attracted to these nonpolar particles, whereas the water is much more attracted to itself. You can also use this to separate based on size, which is called size exclusion chromatography. Separates based on size. So proteins are pretty big. And what happens a lot with proteins when they denature, they form what are called dimers or polymers. So if I have a protein and it denatures by reacting with another protein and sticks together, well, that will travel through differently than just a single protein based on its size. Okay. I want you to really focus, though, on the chemical compatibility. All right. Sorry, I'm going really, really quickly. All right, last one, distillation. So this is separation. What do you think it's based on? Yeah, separation based on differences in boiling point. So what happens is you have a mixture here. One of them preferentially, one component evaporates preferentially based on the differences in boiling point. Then it gets up to this point, the vapor travels here. What do you think this is for? Yeah, cooling it down. This is a condenser. So to cool down. and then collect it as a liquid. So what you do is you take substances that have different boiling points, and these are used to separate liquids. So you boil, one component comes off preferentially, it travels up your distillation column, it cools down so you get below the boiling point, and it condenses and you collect it as a liquid. So theoretically you could separate the two just by boiling one off and then cooling it as it comes down. This is how gasoline generally is separated into its components. So you have these enormous, like 100+ foot columns to separate gasoline. So the way you do that is you have 20 or 30 individual stages of distillation, and you can put each one of these is a stage, and you can take off, say, gasoline here, or heavier components here. So you can separate the materials out into its individual components. And in terms of crude oil, lots of the components have their own specific uses. I suppose I could have drawn that on the next slide, but I'll leave that next slide blank. You can doodle on the next slide. Okay, that was not what I would consider my best lecture ever. We went a little faster than I would like, not enough time for questions. But doing the problem set, you will probably have a better feel for how these separation techniques are used, and we'll do labs on that involve the first two, not necessarily distillation. But. Okay, we are now done with everything that will be on test 2.